Okay, so today we're going to talk about HashTable, tables, good old HashTables, hash tables with open addressing. If you remember from last time, we talked about hash tables with chaining. I'm going to go through a quick recap on why hash tables are so important, and then we're going to go over to open addressing. So first off, why are hash tables so important? Well, let's see if I can get this video going. Let's go ahead and compare our different data structures. Which data structures have we done so far? Let's see who remembers. Arrays. All right. So show us. Linked list. Perfect.
Double linked list.
Oh, we're going to keep it right there. Stacks. Queues, which are an abstract.
Binary search tree.
All right, so we got
Binary
binary. We're going to do binary search tree.
Binary tree.
Binary. We'll keep it with the binary search tree because that's the whole point of binary tree. And then we have hash tables. We also have the heap actually. So let's go and keep heap up there. And then now we have hash tables. Now the reason I didn't put stacks up there is because the stack is usually implemented with a linked list or an array. Same thing with the queue. So these are really the basic ones that we've talked about so far. So we're going to go ahead and start looking at the different operations. Okay. So first off, random insert. I'll just call it that. It's really insert, but I'm calling it random just to say it's not necessarily at the end. How long does this take in a big O?
O of n for array.
Yeah, it's going to be O of n for an array because you have to find it, and even if it's sorted, that'll take log n, but once you get there, you may have to shift the whole array down. So it's pretty much O of n no matter what. How about a linked list?
Is that O of 1?
O of 1 to add it once you have found the location, but to find the location is O of n. Okay. Binary search tree.
And log n.
Where do you get this n from? There's usually one answer with binary search tree.
Log n.
Log in. Right, because you just go down the tree until you find the location, and then you just put it there. So it's just log in. All right, heap.
Log n.
Right, it's log in. You add it to the end of the array, and then you sift up, which could take log in. Hash table. Ooh. We need to insert something.
I don't remember.
What's the first thing we do? We calculate from the key to get the index, right? All right, and what's the complexity of that operation? O of
1.
O of 1. All right.
The worst it could be is O of n.
Well, hold on. We're adding.
Yeah.
So that goes to a location, and then we have to add it to the end of a linked list, which is
O of n.
O of. Well, we don't have to go through the linked list.
Oh, okay.
We just add it.
Yeah.
So it's O of 1. So O of 1 plus O of 1 is
O of 1.
O of 1. So whoa! Hey, look at this. Hash tables are
Pretty fast.
looking great right now. Now, just to make it fair, I'm going to call it optimal insert. And the reason I'm putting this up here is to show that there is a point to using linked lists and arrays. So if it was an optimal insert for an array, it would be at the very end, which is usually O of, well, it's either O of 1 or O of n, right? So I'm going to put O of 1 or O of n. So normally it's O of 1, unless you got to resize the array, then it's O of n. Linked list, it's always O of 1. Binary search tree,
Log n.
log in, yep.
That's like that.
When in doubt, that's the answer. It's just FYI. Heap,
Log n.
log in. By the way, a heap is a binary tree. It's not a binary search tree. It's a binary tree that has to satisfy the heap property. So just keep that in mind. That's really a binary tree. Hash table, O of 1. All right. Now, just going to say remove. I'm going to go again, random remove. All right.
So, O of N.
O of, yeah, O of N.
Also O of N?
Yeah, it's also O of N.
Log in. Log in.
All right, we're gonna have to find someone else to answer these questions. All right, random remove on a hash table. Ooh. Ooh, here we go. What's the average case on a random remove? So you have to find the key, right? And that's an O of. So you convert the key to an index using the hash function, and that's O of 1. O of 1. Now, we're thinking optimal. That's going to put you into an index, correct? Into a linked list. Hopefully that linked list size is 1, in which case trying to find it in that linked list and removing it is an O of 1 operation. Okay.
Ludicrous. Ludicrous.
Ludicrous speed. What is it in worst case? O of N, right. Because if everything hashes to the same location, you have to go through that whole linked list, find the piece, and then remove it. Okay. Well, I mean, hash tables still look pretty good overall. We'll go with optimal remove again.
O of 1 or O of N?
O of 1, there is no O of N because if you're just removing it, you're not having to create new space. You just decrement the size, right? Linked list, O of 1. All right, someone besides David. Binary search tree.
David.
Matt. I keep calling you David.
No.
You are always David in my head. I don't know why,
Is there
Matt.
a David that looks like me?
Look at me again. Yeah. Sorry, mate. Matt.
Mate.
I always call you Mavid. It's what I almost have.
Apples.
All right, someone besides Matt.
Log in.
Log in. All right.
And log in.
Okay. And then if it's optimal remove, the linked list is hopefully size of 1, which would make it O of 1. Okay, great. Wow, this is looking good. All right. How about search? If the array is ordered or sorted, what is it? Someone besides Matt. Or unsorted, you can tell me either one. How long does it take to find something in an array?
O of N.
If it's unsorted, it's O of N, right? So that's actually the worst case. If it is sorted, what can we use?
Index.
Not so much index, but
It would be log in.
login, because we can use a
We could jump into, we start with a binary search.
binary search, because we can start in the beginning, and if it's greater than go to the upper half, otherwise we can go to the lower half. So in that case, it's login then. All right, linked list. Trying to search it.
O of N.
O of N. It's always O of N. Yep. Binary search tree. Trying to search it.
Log in.
Log in. Heap. Wait, yeah, heap. Oh, tricky. Think about it. You're
And log in.
Where do you get this from? Trying to search a heap. How long does that take?
Log in.
So it can't be login. Well, how would you do it login? Let me. I don't see how. You can't be done login. Remember, it's a heap. It just has a heap property. So if you're at the beginning, you don't know whether to go left or right, because the numbers. It's just the immediate numbers are greater than. So there could be some mix up in between. So in other words, you have to search the whole heap, which makes it O of N. hash table. You need to search the hash table. So you're going to find the key, right? Go to the index,
Search the list.
search the list. So on the average case, it's, if the list is size 1, O of 1. In worst case, it's O of N. I heard it.
Try to slip it in there.
Tried to slip it right in. All right, let me think if there's another category we need to look at here. We got insert, remove, and search. All right.
Just looks like HashTable's pretty solid.
Yeah, hash tables are looking pretty good. Until, okay. Now, well, hold on. So, from looking at here, on the average case, hash tables are O of 1, which is great. Hence why a lot of times I've been told when in doubt, just use a hash table. It'll probably get you what you need. Although, it can deteriorate to an O of N. So, will someone tell me why you'd want to use a binary search tree over a hash table?
For searching and remove.
What's that? So we got random removal, right, log in versus O of 1 or O of N. Right, so on average, the hash table would be faster, except for these couple of cases. So the question is, this is a tough question. Why would you want to use a binary search tree over a hash table? In what situation would you want to use a binary search tree over a hash table? And let me put the word balanced up here.
If you were doing a lot of searching.
You're doing a lot of searching. Okay. Well, most of the time you're going to get back O of 1, right? So if you averaged it out over the long run, even though you might have a couple of O wins, the hash table will probably still win. Good morning, Jonah.
Good morning.
All right, so since you walked in here, in what situations would we want to use a balanced binary search tree over a hash table?
Balanced binary search tree over a hash table when there's not really a lot of elements.
There's not really a lot of elements. Good guess. Okay, let me help you out. Which of the two data structures is more consistent?
Binary search tree.
Binary search tree. When would you want a data structure to be very consistent?
Security purposes.
Okay, security, that's a good guess. Right, okay. You want it to be a secure situation. Okay, I see where I think I understand where you're coming from. Another example would be any type of medical equipment, like if someone's life depended on it, or any type of real-time system. The whole category is real-time systems. Anytime you need to guarantee that something will complete in a certain amount of time, you need your data structure to be consistent. Hash tables are not consistent. On average, they're very fast, but they're not very consistent is the issue. So in a real-time system, you're going to gravitate more towards a balanced binary search tree because you know how long remove is going to last. You know how long the search is going to last, as opposed to a hash table where it could be fine, or all of a sudden your plane crashes or something, right? Something drastic could occur. Does that make sense? Why you'd use one over the other? Great. Another great example is databases. In a database, every time you do an operation, you're basically reading from the hard drive, which is a very, very slow operation. If you're trying to service a lot of things, this O of N is going to happen, and when it does, it's going to probably overshadow all your O of 1 operations. So that extra time you take a lot of operations is going to really slow down your whole machine. So that's another situation where you want it to be consistent so you can predict how many machines you need and scale up to your load is another great example. Now, while I'm pointing all these situations out simply because the hash table, hopefully you can tell from this column, really is, in general, the data structure you should go to first. You know, when in doubt, just use a hash table or a hash set. But keep in mind, binary search tree or a tree set, as you will sometimes encounter, is still a very viable option in certain situations. All right. Any questions about this? Great.